You might already be aware that voestalpine is a world-leading steel and technology group. But did you know that our high-performance metals division is also a reliable long-term partner to the plastic injection molding industry? We offer tailor-made solutions for companies such as injection molders and tool makers, as well as for plastic part developers or designers. Join us now to explore our holistic approach to pushing boundaries in injection molding, demonstrated through a coffee cup mold that showcases new horizons in mold and part design. It combines long-term know-how in engineering design with advanced tool steels and manufacturing technologies to achieve remarkable productivity improvements. So how did we achieve these improvements? From engineering design to ready-to-use cavity inserts, we can improve tool performance, reduce costs, and unlock new possibilities in part design. Our simulation-based design approach for conformal cooling optimizes cycle times and part quality. Additive manufacturing offers maximum design freedom in conformal cooling layouts of tool inserts, sensor integration, and weight reduction. By combining Böhler or Udderholm tool steel powders, material-specific process parameters, and optimized heat treatment routes, our additively manufactured tool inserts reach up to 99.997% density, ensuring mechanical properties comparable to bar stock materials and enabling even high gloss polishing. Due to our high standards and expertise in tool steels, we guarantee the outstanding quality of our tool inserts. Additionally, we provide specific recommendations for machining and finishing to ensure reproducible results for your high-demanding applications. Eschmann Textures provides a wide range of surface texturing technologies to create customized, visually and haptically appealing surfaces. Ultra-short pulse lasers enable the creation of even the finest structures with a perfect interplay of design and functionality. Improved cooling performance allows precise control of wall temperature and superior molding of microstructures without compromising dimensional stability. Tailored coatings provide wear resistance while preserving tool functionality and optical appearance. iFiller coating optimizes surface properties, improves wear resistance, and incorporates innovative features for tool longevity. By incorporating conformal cooling and optimized additive manufacturing materials early in the coffee cup mold design, we reduced cycle times, enhanced part quality, and maintained tight tolerances. Our holistic approach embraces voestalpine's commitment to sustainable production. Our sustainability platform Inspire helps our customers to set new environmental standards and reduce their carbon footprint. Discover how the innovative design behind the voestalpine coffee cup and our technologies can benefit your projects. Contact us now to get started.
voestalpine, one step ahead.
Good morning, everyone, and good afternoon. Moving to our webinar, which is on how SimForm enables early break-even validation for conformal cooling. Today, myself, Anurag Thakur, I've been moderating the webinar. And we have two presenters, Mr. Christopher, he's from Maya, our guest presenter, and Mr. Johannes. He's from our product managing team for additive manufacturing. We welcome both for the webinar as the presenter for the webinar. Today's webinar will be for 45 minutes. After 45 minutes of presentation, we would have 10 to 15 minutes for question and answer round. You can send us your question and answers into the question and answer chat box or the chat box separately, which you can find it on the top of your screen. So you can enter the screen. You won't be able to unmute yourself to avoid disturbance. So please, whatever questions you have, you can enter it into the chat box. Now I welcome Mr. Christopher for him to introduce Maya.
Thanks for the introduction, and thank you for having me as a guest speaker for this webinar. So my name is Christopher Blake. I'm a Director of New Product Development at MyHTT. I've been with the company for almost 18 years now, and I've held a number of roles, including applications engineer, product manager, and solutions architect. But now I'm in charge of our innovation business, introducing new products and new technologies to the market. So a quick introduction about our company. MyHTT is a global engineering solutions provider. We started out in the early 1980s, developing a single thermal analysis product that we offered to the space industry. But we've since grown quite a bit, and now we offer three complementary lines of business. First of all, we have our Maya authored software, which is primarily 3D simulation software that's used in the aerospace, electronics, and manufacturing industries. Then we have our expert engineering services, which includes running complex simulations, thermal CFD, structural analysis, electromagnetics. We deploy enterprise PLM. We also do custom software development and enterprise, industrial, and agentic AI services. And then rounding this out, we also offer a number of partner products through our relationship with Siemens Digital Industries. So what we end up doing is we combine these capabilities into, an overall solution that is holistic and very tailored to what our customers are looking for. So during the course of today's webinar, I'll be primarily showcasing the software we developed for the plastics injection molding industry, which is called SimForm. SimForm is essentially mold simulation that everyone can use. In as little as 15 minutes, you can set up and run a simulation in order to evaluate not only the temperatures of your plastic part, but also throughout the mold, throughout the cooling cycle of your plastic injection mold. And you can use this information to determine the best locations for your cooling channels and to evaluate and compare the time it takes to cool your part down in order for it to be ejected. We primarily target users throughout the value chain in the plastic injection molding industry. Mold makers use our software to ensure part quality with uniform temperatures and minimize the number of hotspots. Injection and compression molders, for that matter, can use our software to help optimize the production process, reducing cycle time. And our upfront simulation capabilities enable OEMs and part suppliers to help orient and direct the design of their plastic parts and try and minimize the number of engineering iterations in their designs. So ultimately, you're saving time and money by avoiding over designs, too many redesigns, catching problems too late in the development process, reducing your cycle time, and in particular, SimForm is particularly useful at that stage where you need to justify the use of more expensive cooling techniques like high conductivity inserts or the use of 3D printed conformal cooling inserts, which, as it happens, is the main theme of today's webinar. So quickly about what is unique about SimForm. Well, first and foremost, it's an entirely cloud-based simulation package. No install is required. Simply go to your web browser, log in, and you have access to the software and can leverage the compute power of graphical processing units in the cloud. We primarily target design for manufacturing workflows so that you can easily integrate your simulation practices earlier in the process, enabling designers and engineers rather than only simulation specialists to have access to simulation. And then last of all, we provide generative design capabilities to really accelerate the design of your injection molds. And again, we'll talk about that in a few moments. And with that, I'll pass it over to Johannes to start out the webinar.
Yeah, thank you very much. And I want to start with a question. And the question is, are you still producing or are you already productive? What does this mean? Just because a mold is on a machine and the machine is running doesn't mean that you are productive. If you can save 10 seconds or 10%, 20%, 50% of the cycle time, then you are really productive. And that's important, that with conformal cooling, you can change the productivity. And that's more the biggest advantage that we achieved in the last years, to really shorten the cooling time, because we have a close contour conformal cooling. And of course, in the end, a shorter cooling time ends up in a shorter cycle time. And this ends up in a cost reduction. Another important factor is that because we are using powder materials that are corrosion resistant and wear resistant, we really have an extended lifetime. So we can go for millions of shots, and that's proven in various applications. With a conformal cooled insert, you don't need to worry about lifetime. It's really, really great what you can achieve there. More and more important, get the improvement in quality, because you have a better thermal management, you reduce the scrap rate, and you get tighter tolerances and a more homogeneous temperature distribution. And this is also beneficial for your products, of course. What we are not talking about, but I briefly want to mention, we can also functionalize in the AM process, like for venting, we can implement venting structures, or we can the sensor position where you need it for your process. Sustainability is also an important factor. If you create less scrap, tighter tolerances, and you have cost reduction, it also gets more sustainable for you. And depending on the mold and what you compare, you can have a time and cost saving. Probably that's more just for multi-cavity molds, 8, 16, or even 96 or even more cavities. There, if you compare the manufacturing process, you can save time and money. This as a brief introduction. Today we are talking about the medical tray. So here you see the plastic part. You see the size of 70, 115, 42. In weight, it's roughly 14 gram. We have wall thickness from 0.8 roughly up to 1.6 millimeter. The plastic is a PP. We have some features integrated. You see here those ribs for stiffness, and there is a flatness requirement, and also needs to be a high gloss finish So good surface properties, and target is that we get 2 million parts per year. And now for the first analysis, I hand over again to Chris.
Great, thank you. So I think Johannes was kind of alluding to this, that the cooling phase can take up to 80% of the injection molding process. Not to mention that if you have insufficient or uneven cooling, this is one of the main drivers of part defects or insufficiently injected parts. So this is why we are motivated to try and optimize cooling with conformal channels, if we can improve that part quality and reduce that cooling time and thus the cycle time. But before we invest the engineering time needed to actually design those conformal cooling channels, we can start by using quick simulation to set ourselves a reasonable cooling time target, as well as kind of direct the location of our cooling channels to the most important regions, while also estimating the potential financial benefit of conformal cooling so we can make a good engineering decision. So to do this, we can start by employing a generative design technique that is a feature of our software SimForm, and I'll explain a bit the technique and how it works, then show some results. So first, the user uploads their, I should say, takes their CAD representation of the plastic part, and then specifies some design constraints. These are primarily the safe distance at which you can offset your cooling channels from the cavity surface, as well as a target channel diameter. The algorithm that is fall is going to offset the surface by that safe distance, and then given an assumed uniform cooling is going to predict the cooling time that is needed to make the part safe to eject out of the mold. Then we follow an iterative optimization routine that's going to determine the regions where cooling needs to be applied in order to get as close as possible to a uniform part surface temperature within that target cooling time. More uniform part surface temperatures is going to reduce the tendency to warpage for the plastic part. And then lastly, the cooling regions are extracted and then they're prioritized based on the cooling demand or the heat rejection rate of each of those regions. So now we can look at the first simulation that we did for the medical tray. And for this one, we used typical manufacturing constraints for conventional gun-drilled channels. In this case, it was a 6 millimeter diameter for the channels, or about 1/4 of an inch, and a 12 millimeter offset, or about 1/2 an inch offset. You can see on the screen the offset of those recommended regions from the surface of the plastic part. You can also see the relative cooling demand of each of those regions. And I'll show the underside of the plastic part. And it's not surprising that given the offset that we are kind of forced to adhere to, given our conventional cooling techniques, it's not surprising that the regions with the most cooling demand are in the concave areas of the plastic parts. These are the most important. So where there's the narrow concave area inside of the medical tray. Overall, we predict a cooling time of about 8.6 seconds for this design proposal. So here are the actual conventional cooling channels designed, prepared based on those recommendations. Essentially from SimForm, you can export all of those recommended regions to your CAD system and to do a more detailed cooling layout design. Or if you want to iterate more, you can simply create basic channels within the platform. It's as you wish in your design process. In order to cool the concave areas of this medical tray, but still respect the spacing between the channels and how close we can get with our gun drilling technique, we have to introduce these baffles here to bring the cooling water closer to the concave region. So you see it here in the working surface area of the medical tray, and then also in the underside. But we can only go so deep because this is a very narrow area of the plastic part. So we know, unfortunately, we're going to be faced with some non-uniform cooling of the part. So the natural question is, can we do better than this? Well, if we consider 3D printing as our manufacturing technique for the cavity and core inserts, we can be much more aggressive with our cooling strategy. So here we can really tighten the manufacturing constraints, in this case to a 2mm channel offset and a 2mm channel diameter. So this drops the expected cooling time to 5 seconds. And it essentially is telling us that we ought to try and surround the part completely with water, bearing in mind, of course, where we're going to need to put our hot runner hot tip and any ejector pins in order to push the plastic part off of the mold. And here's what it looks on the underside. And then as a sneak peek, here is the actual conformal cooling design that we end up with for this plastic part. And you can see it, for the most part, following the offset surface that we used in our preliminary analysis. So based on these preliminary recommendations, we can expect a cooling time of around 8.6 seconds for the conventional cooling design, and a reduction to 5 seconds for the conformal cooling. So already we're seeing a cycle time savings, but now I'll pass it to Johannes to present the financial benefits that motivates us towards the conformal cooling solution, and then how to select the appropriate tooling steel for the ultimate solution.
Thank you, Chris. As Chris told, here is some economic calculation. First of all, most important, the boundary conditions. Like we have an hourly machine rate of 15 euro per hour, and the material cost per part are roughly 3 cents per part. For this assumption, we take a 24/7 production with 85% OEE, and Chris showed the cooling time. We adjusted it, so because you have to open the mold, you have to eject the part. So to be more conservative, we choose here for the conventional cooling 12 seconds and for the conformal cooling 10 seconds for the whole cycle time. And here you see the conventional cost, especially for 2 million parts, and also for the conformal cooling. And if you calculate it, the difference at 2 million shot could be a potential saving of 65,000 euro. And if you are looking for the production time that is needed, conventional, with this boundary conditions, you need 327 days, and with the conformal cooling, you need 272 days. So there's a difference of 55 days. So if you now made the first evaluation, with SimForm to identify it. Then you made a rough calculation, and basically that's a huge saving that you get. We dive deeper into it, and now I'm gonna explain you how we do the optimized cooling channel design layout. How do we start with this? First of all, it's important, what does the customer want? Does he only want some cycle time improvement or also some quality improvement, and so on and so forth? So in this specific case, it was cycle time, but of course the quality improvement, there are some flatness requirements which also need to be taken into account. Then we need to have a look, how does the injection molding peripheral look like? What do temperature control units do you use? If you have a multi-cavity mold, how are the inserts connected? In this case, we have just a one cavity mold, so that's not that important because we just have one insert. But yeah, if you are talking about the 16 or 96 cavity tool, 32, whatever, it's really important. Then you go on the right boundary conditions with the simulation, and the design needs all of this taken into account. And in the end, it's always a tailor-made temperature control system, which is specified with your needs. And here is just another example. On the left, you see a conformal cooling, but probably a really bad conformal cooling. And on the right, you see a better version of a conformal cooling. You see here 2 liters more per minute with a parallel channel design. And here you also see bad flow. So yeah, here is the flow velocity nearly zero. So conformal cooling does not need conformal cooling. It's important how you apply the conformal cooling. Another very basic example, here you see some drill channels, diameter of 6, and you get a flow rate of 11.6 liter per minute. By just rounding those corners, you increase the flow rate up to 13.3 liters. So with conformal cooling, we always have those flow optimized channel. And as you see it here, this is a drill channel version. The flow rated optimized version can even be more complex. And how complex can it be? You see it here. What we are doing is we have a look at the plastic part. For example, here is the constraint of 4 millimeter from here to here. But 4 millimeter, as you see it here, we can enter into that area. That's not a problem. And that's important how you apply those channels. You see also that there is a parallel connection, and really, really important is that these channels are balanced. Here you see 4 channels, and you see each flow rate of those channels, roughly 4 liter per minute. So they are equally balanced, and you have a good flow rate with it. The comparison to the conventional cooling, here you see a flow rate of 6.2 liter per minute. And yeah, if we have all of those channels, we are more than 70 liter per minute. That's a huge improvement, and not just also for the fixed side, but also, of course, for the moving side. Here we have the buffer and the surrounding channel. You see them here. Together, you get 19 liter per minute. And what's important here with the conformal cooling, we have a lower flow rate, but we are in the areas where the heat needs to be extracted. And that's very important. Flow rate is not always key. It's better if you extract the heat where the heats need to be extracted. And with the conformal channels, of course, you are always closer than with the buffers or with the drill channel version. And again, those channels are also balanced. That's always important. That's not, for example, the green channel gets the majority of the flow rate and the rest is neglected. That's a very, very important factor, and you can compare it to your hot runner system. A hot runner system is also parallel and balanced, and like you do it with a hot runner, we do it with a conformal cooled inserts. Then another important factor is if you have the design. So how do you choose the right steel for it? If you have a look at the mold, there are a lot of stresses, like thermal stresses from the process. You eject with 200 or 300 or even 400, depending on the plastic degree. Then you have, I don't know, 20 degree, 40 degree, 60, whatever degree of water temperature. So there is a gradient. You have also the mechanical stresses like the clamping force. And as you open and close the molds, it's also cyclic, so fatigue strength, which is important. Depending on the plastic, there are certain additives or glass fiber contents which worn out the tool. You had also adhesive and corrosive attacks. For example, the water or the plastic part, the plastic itself can create corrosion in the tool. Coming back to the medical tray, the part requirements that are that the customer uses corrosive water. So we definitely need to go for a corrosion-resistant steel. There's a long lifetime needed. As I said, target is 2 million parts per year, and it should last longer than 2 million shots. The injection temperature is 250 degrees, the ejection temperature 70 degrees, and we need a high polished surface. That's the part requirements, and translated into steel requirements. So we need to get good corrosion resistance. Regarding those cyclic fatigue behavior, we need a tough and the fatigue material. We need a high gloss finish. There is no glass fiber content in the plastic, but still it needs to be a sufficient hardness because that you are not creating any wear. If we are looking now what we have in our portfolio, you see here corrosion resistant grade. So for the medical tray, we need to choose one of them. You all might know, or you all know the 1.2083 ESR material, which is a conventional material. Then we have 3 powders, which are corrosion resistant. And yeah, like the newest one is a Tyrax. Corax and M789 are very good if you have very aggressive water and you need a really, really high corrosion resistance. We have also non-corrosion resistant grade. So typically you use the H11, H13 type, which is this material. And if you want to be tougher, we go for Diver. If you want to be more wear resistant, we go for W360. So for every application, we have the right material solution. In this case, we went for Udoholm Tyrax. Why? Because that's a good combination, a great combination regarding hardness and toughness. So here you see with a M Tyrax, you are around 28 joule notch impact toughness. And if you have a look at the corrosion resistance, here is Tyrax compared to 2083 high temperature tempering. So you see that we even better in a corrosion resistant way. And you achieve 55 HRC with it. So more or less we have the best combination of hardness, toughness and corrosion resistance. And that's also important regarding the lifetime. Another important factor is the quality of the surface. Here are a lot of data. I summarize it. With our material, we achieve SBI A1. If you classify it like this, here I take now the Tyrax. You see RA, RZ, and R max values. And a rule of thumb, if H11, H13 ESR type polishing quality is enough and sufficient, then always conformal cooling is possible. So in this case, we went for Udoholm Tyrax. And now for the detailed analysis and simulation, I hand over again to Chris.
Thanks, Johannes. And let me just advance my slide. Okay, so now what we want to do is, once we've designed our channels, we want to go through the detailed cooling analysis, before we do any production of the mold cavities. So here's what we did for this medical tray. To start out, we performed a fill pack analysis using another cloud-based injection molding platform called Stromusraum. This is a partner of ours at SimForm. And with this, we were able to determine that the maximum cavity pressure is around 35 megapascals, a value that we're going to use later to help estimate the differential shrinkage induced warpage of the part. And the fill time was only about 1/3 of a second. We can see on the screen the animation of the filling process, and there ends up being one weld line, but essentially we get a complete fill this way. We set up the detailed cooling simulations again in SimForm. Now this involved assigning materials to the inserts, to the mold base, the ejector pins, and the components of the hot runner hot tip. As was mentioned earlier, the resin material is polypropylene. For the medical tray, we use the processing temperature and safe ejection temperatures that are noted here on the screen. And on the left, you can see the 4-channel network of the conventional cooling design with the inlets identified 1, 2, 3, and 4. The water from the chiller was set to 40 degrees Celsius, and based on the preceding CFD analyses of the water flow in the channels, a suitable flow rate was applied to achieve a Reynolds number of 20,000. One thing to note is that there is a period at the beginning of your production runs during which the mold obviously is still heating up to a cyclic steady state. So in the simulations, we explicitly simulate this by specifying the number of warm-up cycles. In this case, we took it to be about 20 warm-up cycles. If we did not specify this, you would tend to underestimate the cooling time and predict lower mold temperatures because you're assuming that the mold is at a uniform initial temperature, which we know at the beginning of the cycle is not the case. So here are the results for the conventional cooling design. We can see that indeed our pack cooling time was confirmed to be about 8 seconds. We also determined that the most effective cooling channel is the one that has baffles going into the working surface or the cavity of the medical tray where you actually store things in the tray. But we also noticed that there is unbalanced cooling in the sense that channel 4 on the underside is extracting channel 4, which is the one we're seeing on the screen, is extracting the most heat. And channel 1, which is in the stripper plate, is the least effective. So having extra channels is actually going to increase the manufacturing costs here. So what we can do is use these simulations to decide, okay, do we actually need some of these channels, or can we save on some of the manufacturing process? Another important thing to note is in certain locations, we're actually seeing a through thickness temperature gradient as high as 30 degrees Celsius, just because we can't get cooling into this narrow cavity of the part. And so this is going to, as we'll see later, result in some additional quality issues. Now, if we look at the conformal cooling design, we essentially use the same setup in terms of obviously the resin grade and the number of warm-up cycles. Given the diameter of these channels and the flow rates that were calculated earlier, we're still in the range of a Reynolds number about 20,000. And you'll notice on the left-hand side of the screen here, I've identified the channel numbering. So channels 2 to 5 are within the stationary side of the tool. They're the 4 branches, and then on the moving side are channels 6 through 9. Here are the results. So we've reduced the pack cooling time to 5.6 seconds. That's what's predicted by the simulation. So that's a 30% reduction. So we're seeing already we're confirming that there's a good time savings there. Again, we've confirmed that channel 1 in the stripper plate is not removing much heat, so this is likely an unnecessary cooling channel, or one we could start to think about whether we need it. However, in comparison to the conventional cooling, we are seeing much more balanced cooling in the conformal cooling channels. And most importantly, we're seeing an important reduction in the temperature gradient through the wall thickness of going down to 3 degrees. So quite a significant reduction there, which is going to reduce our warpage risk. On the topic of warpage, to compare the resulting part quality for the 2 cooling designs, we performed this warpage analysis, which takes into account warpage that is induced by differential shrinkage. So taking into account the main contributions of residual stress that is stored within the part just before it's released at ejection time, and then the free shrinkage as the part cools down to room temperature outside the mold. To compute the differential shrinkage, we use a standard PVT curve for polypropylene while the part is still within the mold and above that safe ejection temperature. And then we use a coefficient of thermal expansion for I'll put in quotation marks, the solid polypropylene once it's outside of the mold. Here are the results comparing the conventional and conformal cooling designs. So this is right at ejection, just after the part is removed out of the mold. And I'll advance to the results once it's cooled down to room temperature. Now, don't be alarmed. The warpage has been magnified so you can see it about 15 times. But nevertheless, given the nominal dimension that we would expect if there was perfectly uniform cooling, we are seeing a difference between the conventional and conformal cooling designs. So there is an advantage. We're basically hitting the mark with conformal cooling because we're getting so much more better uniform cooling of the part in this case. So just a summary of the simulation results here. In terms of cooling time, we can drop down from 8 seconds to 5.6 seconds. If we consider some assumptions around the mold closing, mold opening, and ejection times, we're dropping from 12 seconds down to 9.6 seconds when we get to conformal cooling. The through thickness temperature difference drops dramatically from 30 degrees to 3 degrees, and at least we looked at the Z direction warpage drops from 0.3 millimeters down to something that is basically negligible. There is a difference in design effort, obviously, as reported by my colleagues at voestalpine. It was about 2.5 hours to get the conventional design and up to 5 hours to get that conformal cooling design. There's also the additional cost of printing that cavity tool of about 9,000 euros. But despite this, as Johannes will summarize in the next slide, we do get a very interesting economic savings because of the reduction in cooling time.
Yeah, thank you very much, Chris. Here you see the full economic calculation. If we are looking again to the boundary conditions, it's the same as in the first draft. Again, for the production time for 2 million shot is the same, but now we took the cycle time as the calculations from the simulation. So conventional it was 12 seconds and additive it was 9.6 seconds. And in gray you see the difference. You may recognize that this goes below zero. Why? Because we have in the beginning like the 8,800 euro as an invest, as this was a one cavity tool for the conformal cooling. But let's say roughly after 2,500 shots, we have the break-even point, and annually you are saving around 70,000 euro per year. And so that's a huge benefit that you create with the conformal cooling, even if you consider it when you apply a new mold or when you design a new mold. Yeah, it definitely pays off, and there are a lot of projects where it can pay off. And even if you just have, I don't know, 1 million or 1.2 million parts per year, you still have a good business case to implement the conformal cooling with it. Okay, a quick summary from our webinar. So with SimForm, you can really evaluate the cooling concept in an early design phase, and that's important. There are no costly decisions made, but you already get an impression where to put the cooling, and with SimForm, you get the cooling requirements and you can quantify the performance in a really, really early stage. And then you can make a rough calculation. Like also what I showed is a really basic and rough calculation. We can provide you a more detailed calculation. If you give us your numbers, that's no problem. And if you want, we can develop together with you those cooling inserts and apply those technologies. So to summarize it, with conformal cooling, you are more productive and put it there where it makes sense. As in this example, it definitely makes sense. Yeah, thank you very much for listening. And now we are coming to the questions. Anurag, are there questions?
Yes. So probably before I move to the questions, just to repeat myself for those who have joined a bit late, if you have any query, please